Hari Om. In the fifth module of software engineering course, we are currently discussing the white box testing. The different techniques we have discussed, path testing and cyclomatic complexity, how these two techniques can be used to understand the internal structure of a program and how to design test cases. Now in this video, we are going to talk about the graph matrices. Now, when you take the flow graph method that is used for testing, we are interested in finding the independent paths of the flow graph. But the objective here is you have to trace all the links of the graph at least once. At least once we have to go through all the edges that are available in the flow graph. So what we do, we are going to find out what are the different paths that are available and especially the independent paths. And for each independent path, we can design a test case. But if you take the path tracing, it is not an easy task because it is going to subject to errors if you miss even a link in the graph. And not only that, if the size of the graph is increasing, it becomes very difficult to do the path tracing manually. So in practice, what we have to do, we need a kind of data structure which can be given as the input to a software testing tool. You need some kind of automation tool which can generate all the independent parts of your program, and it can guide you in saying what are the different test cases that are available for the program. So if I want to develop such a tool, a data structure called graph matrix is used. I repeat, testing the control flow, using the control flow graph to test the path testing becomes very difficult if the size of the graph increases. So what we have to do, we need to use testing tools. If you want to use the testing tool, you need to develop a data structure which can represent the flow graph, because you cannot directly give the flow graph as the input to your testing tool. You need a data structure. So generally, graph matrix is used as a data structure to represent the control flow graph. A graph matrix is nothing but a square matrix with one row and one column for every node in the graph. And the size of the matrix will be equal to the number of nodes in the flow graph. When I say number of nodes, suppose if you have 5 nodes, then 5 by 5 square matrix you will be creating. If you have 7 nodes, then the square matrix size will be 7 by 7. And it is a tabular representation of the flow graph. Then in the graph, you will be adding weightage to each and every entry, which can provide additional information about the control flow. Okay, this is just a concept on graph matrix. So that is what is repeated here again. A graph matrix is a square matrix with one row and one column for every node in the graph. The size of the matrix is equal to the number of nodes in the flow graph. And this is an example. Imagine if it is going to be a flow graph, I have 4 different nodes and I have 4 different edges also. So if you have a flow graph like this, to the automation tool, you cannot give this flow graph as the input. So what you have to do, you have to represent this flow graph as a graph matrix. How do you represent it? You are going to represent it in a square matrix. Since I have 4 nodes here, I am going to have 4 rows and 4 columns. And what you are going to do, observe the flow graph you have an edge from starting from 1 to 3. So in the first row, third column, you are going to denote the edge name. Then from node 2, you don't have any outgoing branches, so there is no edges represented here. The same way from 1, you have an edge going to 4, so represent it here. From node number 1 to node number 4, you have an edge called C. Then from node number 3 to node number 2, you have an edge B. So from node number 3 to node number 2, you have an edge B. Then from node number 4 to node number 2, you have an edge called D. So from 4 to 2, you have an edge called D. This is how we will be representing a graph matrix. So in the graph matrix, there is a place to put every possible direct connection between any node and any other node. That is the advantage here. Because all the nodes are represented, and from which node to which node you have an edge can also be represented easily in the graph matrix. So I repeat, in the graph matrix, there is a place to put every possible direct connection between any node and any other node. Suppose, say for example, there is a connection from node I to node J. There is a connection from node I to node J, but it does not imply a connection from node J to node I. And all of us know that the flow graph is a directed graph. It is a directed graph. So if you say there is an edge from 1 to 3, it doesn't mean that there is an edge coming from 3 to 1. That is what is specified here. I repeat, a connection from node I to node J does not imply a connection from node J to node I. So here, a connection from node 1 to node 3 does not imply that there is a connection from node 3 to node 1. That is what is represented here. Let us take another example. There is a graph, flow graph, and what is the graph matrix is also given here. You can observe from node 1 you have a connection going back to node 1 itself, and the edge is represented as A. So from 1 to 1 it is A itself. And from node 2 you have two outgoing branches going to the same node. Two outgoing branches going to the same node, right? So node 2 is having two outgoing branches B and E, but both of them are going to the same node. So you can observe here how it is being represented. So you denote all the edges in the same entry. Then from 3 you have an edge going to 2. So you are representing it like this. From 1 it is going to 3. You are representing like this. So this is the graph matrix for the given flow graph. Let us see another example. This is a little bit bigger flow graph, and you can observe there are 8 nodes available in the graph. 8 different nodes are there. If the nodes are n, if there are n number of nodes, then you will have n by n square matrix. This is the square matrix. For 8 node flow graph, you are going to have 8 by 8 graph matrix. And you can see here from node 1, you have two outgoing branches, 1 to 4, the other one to node number 3. So the edge from 1 to 3 is denoted as A, and the edge from node 1 to 4 is denoted as I. Right? The same way from node 5, if you observe from node 5, there is only one outgoing branch to node 6, which is represented as M. If you take node 7, there is only one outgoing branch coming from 7 to 8 and it is represented as E. Whereas if you take node 6, it is having 3 outgoing branches. 3 outgoing branches. One is going back to 6 itself, denote it as L. So it is denoted as L. One is going back to 5, denoted as C. And one is going to 7, denoted as D. So this is how we will be deriving the graph matrix for the given flow graph. So your graph matrix is nothing but a tabular representation of a flow graph. Your graph matrix is nothing but a tabular representation of a flow graph. This is the tabular representation of the flow graph. Now what we are going to do, we are not going to use this graph matrix directly for our testing process because it is of no use. It is just representing what are the edges coming from each and every node. Now what we are going to do, for these graph matrices which are denoted with edges represented, we are going to assign weight to each entry of the each entry in the graph, and the graph matrix can be used for evaluating useful information required during testing. So you are going to assign weights to each entry in the graph. Say for example, there is an entry here, there is an entry here. For this entry I am going to assign a weight value. For this entry also I am going to assign a weight value. So instead of representing them with edge name, I am going to assign weights to each and every entry. So these are the different entries that are available in the graph. So for each entry you are going to assign a weight. So when you assign weights to each entry in the graph, then it can be used for evaluating useful information. So a graph matrix with such weight is called as a connection matrix. Let us see, this is the graph matrix. We are going to assign weights to the graph matrix. For example, if I have a connection from node 1 to node 3, I am going to assign weight value as 1. And if there is a connection from 1 to 4, I am going to assign a weight value as 1. So if the connection exists, I assign the weight value as 1. If there is no connection, I assign the weight value as 0. Okay, and remember you can have other properties also assigned for link weights. For the time being, we are going to take 1 and 0 if the connection exists and if the connection does not exist respectively. So this is the connection matrix for our example graph. This is the flow graph. Now the flow graph is represented as the graph matrix, and now this graph matrix is represented as the connection matrix. How do you represent it? I have a connection here, I have a connection here. So these two entries will be assigned with value 1, 1. The same way, you have 2 entries here and 3 entries here in 6. You can observe in the connection matrix 2 entries and all the 3 entries are with values 1. Now what we are going to do, to calculate the cyclomatic complexity, we can make use of this connection matrix. So this video just shows you how a flow graph can be represented as a graph matrix and how the graph matrix can be converted into a connection matrix. So we will be discussing how the connection matrix can be used for the calculation of cyclomatic complexity in the upcoming video. Thank you.